Hi everyone, this is a video where I'm going to go over some secrets of absolute values when dealing with calculus, limits, and derivatives. I gave you a QR code and a link for a worksheet, and I'm going to now go over the 9 problems on that worksheet. All right, let's start. I promised a secret to doing absolute values, and this is it, that you can always rewrite the absolute value of x as a piecewise function. That is to say, if I've got the absolute value of x, that is the same as plain old x when it is not negative, that is to say positive or 0, and it is equal to the opposite of x when x is less than 0. So I've rewritten the absolute value of x as a piecewise function. That's going to give us insights into these next problems. Let's look at the first one. It's actually reaching back into your pre-calculus knowledge, and this might be the hardest one on the sheet. I don't know. We've got a function that is the sum of two absolute value functions, absolute value of x, absolute value of x plus 2. All right, so to write this without using absolute value signs, I'm going to use this secret that I just gave you. The interesting parts of this function, I think, are where, let's see, at x equals 0, this first function changes signs, right? So x equals 0 is certainly a place we need to examine. Also, the second part of the function, x minus 2, changes signs at x equals 2, right? Above 2, absolute value of x minus 2 is positive. Below 2, absolute value of x minus 2 is negative. All right, so how can I use this secret to rewrite the function? Well, it is the sum of two things, the sum of two functions. So below x equals 0, down in this area, when I graph it, both of those absolute value expressions are going to be negative. So I'm going to rewrite this function f of x as, down in the below 0 part, I'm going to write that as the opposite of x plus the opposite of x minus 2. Both parts of that function are negative. That is when x is less than 0. Similarly, when x is above 2, both parts of this function are positive. So for x bigger than 2, I'm going to say this is x plus x minus 2. I'm just adding the two pieces together. It's in between 0 and 2 that we've got something interesting happening. In between those two parts, the absolute value of x is positive, but the absolute value of x minus 2 is negative. So how am I going to express that with my piecewise function? I'm going to say that the first function is just itself, absolute value of x, but the second function is its opposite, x minus 2. Come on, Creighton, x minus 2. So that is for 0 less than x less than 2. All right, now it's just a little algebraic simplification, and I will have it. Negative x plus the opposite of x minus 2 is the same thing as minus 2x plus 2 for x less than 0. When I combine x plus negative x minus 2, that's going to be x minus x. That cancels out. I will simply have a positive 2 between 0 and 2. And finally, I've got x plus x minus 2. That gives me 2x minus 2 for x bigger than 2. Great. So that is my function rewritten without using absolute value signs. And if I'm quite generous, I'll go ahead and put up a graph of this function so you can see that kind of makes sense. All right, now we're going to move into the calculus part of this. We are going to find the limit of the absolute value of x over x. All right, so remember the secret. This is going to show up so many times. The absolute value of x can be rewritten as a piecewise function. So I'm going to rewrite the absolute value of x over x as a piecewise function. I'm going to write it as plain old x over x when x is bigger than or equal to 0, and I'm going to write it as negative x over x when x is less than 0. So what does that give me? That says that this function is actually equal to 1 when x is bigger than or equal to 0, and it's equal to negative 1 when x is less than 0. Great. Now, of course, the limit is at the interesting point, right? It's at x approaching 0. Well, based on the simplification we've done, approaching x, as x approaches 0 from one side, it's 1. As x approaches 0 from the other side, it's negative 1. So we can say that this limit does not exist. There's our answer. We cannot calculate that limit. All right, on to number 3. Same secret, same kind of approach. I'm going to rewrite this function to be a piecewise function with that absolute value. I'm going to rewrite it like this. When x is bigger than 0, when it's positive, I'm going to have x minus x over x. That's for x bigger than or equal to 0. And it's going to be negative x minus x over x for x less than 0. In other words, I'm replacing absolute value with x and with negative x in appropriate places. What does that simplify to? Well, x minus x over x, that's simply 0 for x bigger than or equal to 0. And negative x minus another x is minus 2x over x, which simplifies to minus 2 for x less than 0. Just as above, the limit is at x going to 0. From one side, that value is 0. From the other side, that value is negative 2. So once again, this limit does not exist. Because the two-sided limits aren't the same. Rock! Let's move on. The next one, I'm going to use the same secret. We want the limit of absolute value of x minus 2 over x minus 2. Well, where does the absolute value change from being positive to negative? That is at x equals 2. So when I rewrite this, I'm going to write it as x minus 2 over x minus 2 for x bigger than or equal to 2. That's where the absolute value is positive. And I'm going to write it as the opposite of x minus 2 over x minus 2 when x is less than 2. Great. Can simply say that the top one, x minus 2 over x minus 2, that's 1. And the opposite of x minus 2 over x minus 2 is negative 1. So it looks like, and as I've said in all the other ones, the limit is at the interesting point where the left and right hand limits don't agree. So what can I say? That this limit as x approaches 2 doesn't exist. From one side it's 1, other side it's negative 1, does not exist. Now, looks like every time we've got an absolute value problem, we can just say that the limit doesn't exist. Let's see if that pattern holds. On to problem number 5, where I'm finding the limit of absolute value. Let's see, limit of the absolute value of x to the third over x. I want to use the secret that I gave you. I want to use replacing absolute value of x with that piecewise function. Right here, I've got absolute value of x to the third power. Not sure how to approach that using the secret. So let's see what we can do. The absolute value of x to the third, well, what values of x might we have? We might have positive values of x. We might have negative values of x. Let's just pick one. If x is positive, let's say x is 2, the value of this expression, absolute value of 2 to the third, is the same thing as the absolute value of 8, which is 8, which is actually the same thing as the absolute value of 2 to the third power. What I'm trying to say is when x is positive, we can move the power to the outside. If x were negative, what would I get? That would be minus 2 to the third power, absolute value. That's the absolute value of negative 8, which is 8, which is the same thing as the absolute value of negative 2. Take the absolute value and then write it to the third power. So what I've shown is that the absolute value of x to the third power can be rewritten as the absolute value of x to the third power. Why would I rewrite it like that? Well, I want to use the secret. The absolute value of x can be written piecewise. Now I've got something with the absolute value of x in it, and I'm in business. This is the same thing as the limit as x goes to 0. I really want just a plain absolute value, so I'm going to rewrite this as absolute value of x to the second power times absolute value of x over x. And what do we know about squaring? It always gives us positive numbers, right? The absolute value of x quantity squared is the same thing as x squared. So I'm going to rewrite it like that with my limit. And x squared on the top and an x on the bottom, I can cancel the squared and the x, and I'm left with the limit as x goes to 0 of x times absolute value of x. All right, I'm now at a point where I can use that secret that I gave you. I can use the fact that absolute value of x can be rewritten as a piecewise function. How can I rewrite this function? Well, it's going to be x times plain old x when x is bigger than or equal to 0, and it's going to be x times negative x when x is less than 0. Boy, I'm saying x a lot. I think you see what I'm getting at. I've split the function into two pieces. So this function is x squared when x is bigger than or equal to 0, and it's negative x squared when x is less than 0. And we are worried about the limit when x approaches 0. All right, so what is this function if I approach 0 from one side and approach 0 from the other? In this case, I get 0 from both sides, right? When I plug in 0 as I go from the positive side, I would be plugging into this top part, and I would get a 0 out. When I'm approaching from the negative side, I'd be plugging into the bottom part, which is also a 0. So the limit as x approaches 0 is 0 from both sides, so this limit does exist, and it's 0. This limit is 0. And once again, I might put a copy of the graph of this function up so that you can see the limit exists and that it is 0. Great. That's enough limits. Let's move on to differentiation. My problem here wants me to differentiate f of x equals something with absolute values in it. Well, I'm going to use my secret again, the absolute value of something. I'm going to rewrite this function as a piecewise function. This is going to be x squared minus 4 when x squared minus 4 is positive, right? I've got the absolute value of something. When the something is positive, I can remove the absolute value bars. So this is true when x squared minus 4 is bigger than or equal to 0. And it's the opposite of x squared minus 4 when x squared minus 4 is less than 0. And now I'm just going to do a little moving around to make this look a little better. I can rewrite this piecewise bit as x squared minus 4 on the top. And when I distribute the negative in, I'll have a 4 minus x squared on the bottom. Great. And I can rewrite the conditions for this piecewise function a little bit. I can move that 4 to the other side in both of these conditions. So it's x squared minus 4. Oh boy, I wrote that wrong. When x squared is greater than 4, and it's 4 minus x squared when x squared is less than 4. All right, that's still not sitting right with my mathematical brain. I want the conditions to simply be conditions on x. So when is it that x squared is bigger than or equal to 4? When is the square bigger than or equal to 4? Well, that is where x is bigger than or equal to 2, or where x is less than or equal to negative 2, right? In both cases, x squared is going to be bigger than 4. And for the bottom piece, when is x squared less than 4? Well, that is when x is strictly between minus 2 and 2. So there we go. That's our derivative. Oh, no, it's not our derivative. What am I talking about? That is simply our function. Now I can take the derivative. All right, so the derivative of x is simply the derivative of each piece. So that's going to be, let's see, the derivative of the top is 2x. The derivative of the bottom is minus 2x. And these conditions are still true. So the top part is the derivative when we've got that condition, and the bottom part is the derivative when we've got this condition. So that's my final answer. That's the derivative of absolute value of x squared minus 4. And guess what? Later on, problem number 9, I'm going to develop a formula for taking the derivative of something in absolute values. You'll see. It's fun. Okay, problem number 7. I'm asking you a question about differentiability. Is this function, x times absolute value of x, differentiable at x equals 0? Well, I don't want you to forget our secret because it's kind of the theme of the episode. I can rewrite this function f of x as something piecewise. What is it going to be when I rewrite it piecewise? Well, x times absolute value of x will simply be x squared when x is bigger than or equal to 0, and it'll be negative x squared when x is less than 0. I'm changing the absolute value of x to be either plus or minus x. Okay, there's my function. What do I need to know to see if it is differentiable? Well, I need to see that the limits exist, that the function is continuous, and that the value of the function is the same as the limit. So let's do that. I'm going to do it using the definition of derivative. I know that's kind of torture, but I'm going to do it anyway because I can. First thing I need to figure out is whether this limit exists. What does that mean? That means the limit as you go from the left, the limit as you go from the right has to be the same. Well, I hope you can see that the limit of f of x as x goes to 0, I'm interested in the point 0, it's going to be 0 when I approach from the right because I would plug into the top part, and it's going to be 0 when I approach from the left because I would plug into the bottom part. So the limit exists and it is 0. What else do I know? I know that the value of the function at 0 is 0 because I would plug that into x squared, I get 0. So what does that tell me? That tells me that the function is continuous at this point. I got limits, I got limits, I got continuity. Now I am going to use the definition of derivative to compute the derivative of this function. What does the definition of derivative tells us? It tells us that the derivative of this function is the same as f of x plus h minus f of x divided by h. And of course, I wrote that wrong. I left out the important part, which is that the limit as h goes to 0 of that fraction. So that's definition of derivative. Once I evaluate this, I will have the value of the derivative at 0. All right, I'm going to plug in 0 for x. Why? Because I am interested in f prime of 0, where x equals 0. Great. This is that limit, and I'm going to plug in a 0 for x. So f of 0 plus h minus f of 0 divided by h. Rock. F of 0 plus h. Well, 0 plus h is simply h. So this is my limit of f of h minus f of 0. Do I know f of 0? I do. I computed it up here when I computed the continuity. So I know that f of 0 is 0. I don't have to subtract anything. F of h minus 0 over h. All right. The limit as h goes to 0. What is f of h? Where would I get that from? Well, I have f of x right here. Just replace it with an h. So f of h is h times absolute value of h divided by h. My h's cancel, and I'm left with the limit as h goes to 0 of absolute value of h, which is 0. What does that tell me? That tells me that the value of the derivative at 0 is also 0. So if I graph this function at x equals 0, I've got something, an inflection point maybe. We'll see when we look at the graph. Problem number 8. Let's see. I'm really belaboring a point about what you already know about absolute values. You know that the absolute value of x is not differentiable at 0, right? The graph of the absolute value comes down to a point, comes to a corner, and corners aren't points of differentiability. So that you should walk in knowing that the absolute value of x is not differentiable. Now I'm asking you to determine the differentiability of f of x equals x cubed. I want to use my secret again. I want to rewrite absolute value of x as a piecewise something. So I can rewrite f as, I can write it as x to the third when x is bigger than or equal to 0. And I can write it as negative x to the third when x is less than 0. I guess I could use definition of derivative, but that seems like more work than I want to do. Let's compute the derivative of this function. That's going to be the derivative of the pieces, 3x squared for non-negative values, and negative 3x squared for negative values. All right, there's my derivative. Is it differentiable at x equals 0? Once again, I need to check my conditions. I need to check that the limit exists at x equals 0, and it does. The limit from the left and the limit from the right are both 0. I need to calculate the value of the function at 0. Well, f of 0 is also 0, so it's continuous at that point. And I could go through the definition, but I'm not going to. I've done it algebraically. So the value of the derivative at 0, well, I'm going to use this top piece because that's where x equals 0, and I get 0. A lot of zeros in this problem, but it works out. I have computed the derivative, I've determined that it's differentiable, and I know the derivative is 0. All right. Question number 9. This is a hard problem. This is not something that you're going to see on a BC Calculus test or even on the BC Calculus exam. This is really kind of a proof. I want us to develop a formula for finding the derivative of anything, any function that has absolute values around it. And I've given you a sort of a hint here. I've said rewrite the absolute value of u as square root of u squared. And think about it, it should make sense that the absolute value and square root of u squared are the same, right? If I take anything, u, and square it, it's going to become positive. I take the square root, I'm back to u, it's just got no sign anymore. Yeah, I have squared anything and taken the square root. Inverse functions, but the sign has vanished. So I want us to rewrite this function f of x. I've given it to you as the absolute value of u, but that is absolutely equivalent to the square root of u squared. That's the hint. And now I want to calculate the derivative of this function. All right, well, you're pretty good with powers, I think, by this point, right? Finding derivatives of powers. Let me change this f of x to be u squared to the 1/2 power. And now computing the derivative using the chain rule might not be so bad. The derivative of u squared to the 1/2 is, all right, what does the chain rule tell me? It says this is 1/2 times whatever's in the parentheses to the minus 1/2. Inside the parentheses, I've got a u squared. The chain rule says I now have to multiply by the derivative of the thing on the inside. The derivative of u squared is 2u. Since u is a function of x, the derivative is actually 2u times the derivative of u. So this is what comes out when I use the chain rule. And what can I do with this? Well, it looks like I can cancel that 2 and that 2. And let's see, I've got u squared to the minus 1/2. That's the same as 1 over square root of u squared times u times the derivative of u. Let's not forget what we're trying to get to. I have given you that this is the formula I want us to wind up with. Am I there? Almost. 1 over square root of u squared. Gave you this hint. Square root of u squared is the absolute value of u. I'm sort of using the hint in reverse. Times u prime, and that is going to give me u prime times u over absolute value of u. And that is exactly what I said the derivative ought to be. Okay, so what, Creighton? Why is this important? Well, I now have given you a way to find the derivative of anything that's inside absolute value marks. Should you memorize this function? No, you're not going to use it again. But you have it, just in case, I guess. It's a weak argument. All right, so what does that tell me? If I've got some function, let's just come up with something. Absolute value of sine x. And I ask you to find the derivative of that function. Well, now you can. You have a formula for it. Our formula says that the derivative of this function is u prime. So the derivative of u times u over absolute value of u. All right, u is sine x. Absolute value of u is absolute value of sine x. And u prime, the derivative of sine, is cosine of x. Okay, so where is this derivative valid? I mean, this is it. I just have to exclude any points that aren't valid. And I notice that there is a denominator here, so I've got a few points that don't have derivatives. Where are they? This function is going to be, I can, think about this as being either 1 or minus 1, depending on the value of sine. So what points do I need to exclude? Well, this thing is going to be either positive or negative. When do I have to exclude a point? All right, well, it's going to be positive when, let's see, when is sine positive? That is between, I'm thinking about my unit circle, sine is positive between 0 and pi, right? So between 0 and pi, the thing I have circled is positive, so this is just going to be cosine of x. And it's going to be the opposite of cosine of x when the sign is negative. So down below, pi to 2 pi. I want you to notice carefully, though, how I've written this. All of my less thans are straight less than. There's no less than or equal to. Because at those endpoints, 0 and pi and 2 pi, sine is 0. So this thing that I've circled is undefined. All right, so I've computed this derivative. Does it even make sense? I contend that it does. Let's look at the original value of the original graph of this function. The normal sine, how does it look? It goes from there up to 1, back to 0, down to minus 1, and then back to 0. So I could draw in the regular sine curve, but I'm looking at the absolute value of sine. So the absolute value of sine looks like that, and it's going to just repeat forever and ever. I'm claiming that there's no derivative at the points 0 and pi and 2 pi, and according to this graph, that makes sense. Remember with absolute value of x, we said that there's no derivative at corners? Well, here's the corners of absolute value of sine x. It's got corners in all these places, so it's not differentiable there, and we sort of saw that that's true. That was a long way to go, but we got there. All 9 problems are solved. I hope this helps you out. Remember, always change your absolute values to a piecewise function when you get the chance. That's it. I will see you next time.